The morning of February 25, 2009, dawned like many others. For the passengers and crew of Turkish Airlines Flight 1951, it was meant to be a standard journey. The Boeing 737-800 registration TCJGE was on its final leg from Istanbul to Amsterdam's Schiphol Airport. The sky was overcast, but nothing that would unduly concern an experienced flight crew. The aircraft was lining up for runway 18R, also known as the Polderbahn. As Flight 1951 prepared for landing, everything on the surface seemed normal. The pilots, engaged in the complex ballet of approach procedures, were communicating with air traffic control. Unbeknownst to them, a silent, insidious failure was already in motion. The approach to Schiphol is a carefully choreographed sequence. Pilots rely on a sophisticated array of instruments and automated systems to guide them safely to the ground. But what happens when one of these trusted instruments begins to lie? This was the precipice upon which Flight 1951 teetered. The journey from Istanbul had been uneventful, lulling everyone into a sense of security. The aircraft, carrying 128 passengers and 7 crew members, was just moments away from what should have been a smooth touchdown. At the heart of the unfolding tragedy aboard Turkish Airlines Flight 1951 lay a seemingly innocuous piece of equipment, the left-hand radio altimeter. This device is crucial during the final stages of flight, particularly during landing. On this fateful day, the captain's radio altimeter was malfunctioning. Instead of reporting the aircraft's actual altitude, it suddenly began to indicate that the plane was at -8 feet. This erroneous reading was a critical input for the autothrottle. The autothrottle system automatically manages engine power to maintain a selected airspeed or flight condition. The system, in its digital mind, was simply following its programming. It received information that the aircraft was at -8 feet and acted accordingly. The problem was the aircraft was still hundreds of feet in the air. The autothrottle, trusting the data from the single faulty altimeter, began to pull the power back. This is a classic example of how a small, localized failure can cascade through interconnected systems, leading to a much larger, more dangerous situation. With the autothrottle system erroneously believing the Boeing 737-800 was just about to touch down, it dutifully executed its programming. The engine thrust levers were automatically retarded to idle. This action was disastrous for Flight 1951, which was still at an altitude of approximately 2,000 feet but descending. The reduction in engine power meant the aircraft began to lose airspeed rapidly. The aircraft, starved of thrust, was now on a trajectory towards an aerodynamic stall. Stall warnings, including a stick shaker, would have activated in the cockpit. However, the response to these warnings was tragically delayed and ultimately insufficient. The aircraft stalled completely and descended rapidly, striking the muddy ground in a field approximately 1.5 kilometers short of the Polderbahn runway. The impact was severe, resulting in 9 fatalities, including all 3 members of the flight crew in the cockpit, and numerous injuries among the 120 survivors. In the immediate aftermath of the crash, the priority was rescue and recovery. Emergency services rushed to the scene, a challenging environment in the soft, muddy field. Once the survivors were attended to and the site secured, the meticulous process of investigation began. The Dutch Safety Board, the organization responsible for investigating aviation accidents in the Netherlands, took the lead. The initial findings quickly pointed towards the malfunctioning radio altimeter and the subsequent inappropriate auto-throttle response as primary elements in the chain of events. The investigation delved into every conceivable aspect: the aircraft's maintenance history, the design of its automated systems, the training and experience of the flight crew, air traffic control procedures, and even weather conditions. The final report, released by the Dutch Safety Board in May 2010, confirmed that the crash was primarily caused by the auto-throttle responding to the faulty left radio altimeter. The report also highlighted that the crew did not react appropriately to the stall warnings or effectively execute the stall recovery procedure. The Dutch Safety Board's investigation didn't just stop at the immediate technical failure of the altimeter, it delved deeper into the very design philosophy of the Boeing 737-800's automated systems. A critical finding emerged: the auto-throttle system, in certain landing modes, was designed to rely on data from only one of the aircraft's 2 radio altimeters. In the case of Flight 1951, the captain's autopilot was engaged, and thus the system was solely dependent on the captain's faulty left radio altimeter. This lack of sufficient redundancy, or a robust cross-checking mechanism for such a critical input, was a significant design concern. The DSB report was pointed in its assessment of Boeing's responsibility. It stated that the aircraft manufacturer had contributed to the circumstances that led to the accident. The report highlighted that Boeing had been aware of potential issues with the radio altimeters and their interaction with the auto throttle system from previous incidents, yet the corrective actions taken prior to the Flight 1951 crash were deemed insufficient. The investigation essentially uncovered an Achilles heel in the aircraft's automation. While the faulty altimeter and the auto throttle's response were the technical triggers, the human element played a crucial role in the tragic sequence of events of Turkish Airlines Flight 1951. The investigation revealed that the flight crew was aware that the captain's radio altimeter had been malfunctioning. However, despite this awareness, they did not disengage the auto throttle system in a timely manner. The first officer, who was the pilot flying, did notice and call out the decreasing airspeed. Yet the critical intervention, a decisive manual takeover and application of full thrust, was not executed with the urgency the situation demanded. The investigation also brought Turkish Airlines pilot training programs under scrutiny. The DSB report pointed to potential inadequacies, particularly concerning the understanding of automated flight systems and the management of emergency situations. The Turkish Airlines Flight 1951 accident underscored the critical need for continuous, rigorous training that focuses not just on normal operations, but also on recognizing and managing automation failures, and effectively transitioning to manual control in complex, high-stakes scenarios. The crash of Turkish Airlines Flight 1951 served as a stark wake-up call for Boeing. The findings of the Dutch Safety Board necessitated significant changes. Boeing initiated a series of modifications and issued new guidance to airlines operating the 737 next-generation family of aircraft. One of the key technical changes involved updating the aircraft's software. Boeing developed and mandated an update to the speed trim system and auto throttle logic. This update was designed to improve the system's resilience to erroneous radio altimeter inputs. Beyond software updates, Boeing also provided new operational guidance and training materials to airlines. The lessons from Flight 1951 were directly fed back into the design and certification processes, aiming to build more resilient and safer aircraft for the future. Despite the official investigation by the Dutch Safety Board and the subsequent changes implemented by Boeing, the story of Turkish Airlines Flight 1951 did not entirely fade into the annals of resolved aviation incidents. In 2020, a bombshell investigation by the New York Times alleged that the initial DSB inquiry had potentially downplayed criticisms of Boeing's design flaws. This journalistic investigation triggered significant political and public concern in the Netherlands. Dutch members of parliament called for the inquiry into the 2009 crash to be reopened. The reopened inquiry sought to determine if all lessons had truly been learned and if the focus of the original investigation had been appropriately balanced between technical design flaws and human factors. The lingering questions surrounding Flight 1951 highlight the complexities and sensitivities involved in air crash investigations, especially when they involve major manufacturers and international interests. The pursuit of truth in such incidents is paramount for aviation safety, but it can sometimes be influenced by various pressures. The renewed scrutiny of the Polderbaan incident served as a reminder that even closed cases can be re-examined if new evidence or credible concerns emerge. The renewed interest in the Turkish Airlines Flight 1951 crash in 2020 was not purely academic or historical. It was deeply intertwined with a far more recent and devastating crisis involving Boeing, the two fatal crashes of the Boeing 737 MAX aircraft. As investigators delved into the causes of the MAX disasters, unsettling parallels began to emerge with the circumstances of the 2009 Amsterdam crash. Both the 737-800 involved in the Turkish Airlines crash and the 737 MAX models featured automated systems that could, under certain failure conditions, take decisive action based on input from a single faulty sensor. The similarities raised profound questions about Boeing's design philosophy and its safety culture. The focus on software fixes for MCAS mirrored in some ways the software updates made after the 2009 crash. But the deeper questions about system architecture and human-machine interface remained. The long-term impact of the Turkish Airlines Flight 1951 crash, when viewed through the lens of the later 737 MAX crisis, extends far beyond the specific technical fixes implemented for the 737-800. It serves as a critical case study in the ongoing dialogue about aviation safety, automation dependence, regulatory oversight, and corporate accountability.